coming. What I want to talk today about is the Kappa architecture and how we actually apply that in the telecom sector. So my name is Ignacio. I work at Ericsson Research. And I'll try to give you an overview of what actually Kappa means and then how we actually are able to realize that into our use case. So keep in mind that this work is done in Ericsson Research, which means it's not production. But we will touch upon some of the latest features that Flink has incorporated. So it might be interesting from that point of view. The proposed agenda, I'll try to answer the 3 what W questions and then how. Try to give you this overview and then try to deep down a bit more into what tools have we used and an interesting topic about streaming that some others have already mentioned, and it was in the keynote, that how we actually handle time in this kind of system, which is quite relevant in our specific use case. And all that, I'll try to do a local demo, so you can actually see what is the result of this analysis and some visualization methodologies that we have used, basically, to monitor what we are doing. So who are we? I mentioned already that I'm from Ericsson Research, but that's already quite wide already. So my particular task, and I'm involved in an organization called Management of Complex Systems, which basically we try to look into solutions that handles analytics and bit of machine learning as well, and then apply that to some business case in the telecom industry and ICT. This project was granted by ICT Europa, and that was basically done in collaboration with the Swedish Institute of Computer Science. So, who is Ericsson? For those who maybe don't know it yet, maybe it sounds familiar to you for the mobile phones that once we used to have, but that's not the core business anymore. Ericsson is one of the main providers in mobile infrastructure and cloud, especially in the telecom sector. And it basically builds not only the equipment, but also solutions on top of it. So it has a wide range of services and operations. And maybe the most important one that is currently being advertised a lot is the TV platform. So actually, Ericsson gives services to many of the players that want to give television on demand, for example. So some numbers I put there, like 2.5 billion are the number of people that are currently running through Ericsson networks. It's spread over 180 countries, and this is actually something that is going to grow exponentially. Some of you have already mentioned this IoT dimension. It's coming, and it's primarily affecting some of the operators that are currently operating in many countries. I mean, how this network can actually support not only the 2.5 billion globally, but it will be, according to estimation, it can reach about the 50 billion connected devices in 2020. So we actually need to find some clever ways of handling this infrastructure that actually can manage all this traffic and requirements that this new situation is imposing. So to put you into some numbers today, this is what a medium-sized operator would look like in terms of data. So as you know, people are increasingly changing from desktop to mobile. So that actually not only the IoT, but also the user are imposing more things into the networks. And that basically translates in a daily day a sum of data ranging from 10 to 100 terabytes a day. That data that can be generated. And that means in real-time rate around from 100,000 events per second to 1 million events per second. So how can we actually analyze such amount of data and get insights out of it in some sort of acceptable delay? Okay, we have this motivation. How can we actually find a solution for this? So that's why I want to now to hook a bit with Kappa architecture. So this is where it comes, why we actually choose Kappa architecture to solve this problem. So Kappa architecture have, I don't know how many of you have heard about it already? Okay, good. So it has four main concepts that are quite interesting in this setup. So the first and very first thing that they say is that everything is a stream. So in the Kappa architecture, whatever data source that you have, it will be coming as a string. That's one of the first. Then the second one and the third one, which are quite related, is that you need to have immutable data sources, and that those should, the system should be able to replay those in case something happens. So, for example, for us that we want to analyze on the system and so on, we need to keep what was the situation when something happens. So, I mean, we don't want to basically have a stateful data that we change and then we come back again and then we, okay, where was the problem before? Because that was overridden. So the Kappa architecture, what it says is like, okay, you should be able to replay, and then when the code evolves, actually you should be able to basically reproduce the same results that you used to have before. And then the last one, and this links a bit with some of you that heard Lambda architecture. Lambda architecture basically says that you need a stream and batch, while the Kappa architecture says that, well, that's because we don't really have a good stream engine yet. It's supposed to be just a single framework that does the analysis for you, and you only have to maintain this single code and not replicate, basically. So, following these four principles, what have we done? I will go. So what we are interested in, and I will show you now, is that we will take a simple setup. We have a running cloud with 32 machines. We will extract data from it, let's say logs and metrics and this kind of system performance metrics. We want to analyze it, and then basically we want to see what kind of relevant information we're interested in. We don't want to see the 10,000 records that are being generated, but rather say like, okay, this has a frequency of this amount and this has another thing. So we want to see basically the insight and then apply some anomaly detection, which is a bit more apply basically a more advanced machine learning that can basically say if the system is deviating from a good state or is behaving in an abnormal state. So for that, I will just let me start the demo. So I will just switch back and forth. For the demo, I just mentioned that I will use Vagrant. I don't know if some of you are already familiar with it. This basically will boot me some, it will be 2 VMs. I will go into details later what this local setup is look like. But from the time now, I mean, you will basically put Kafka and then some playback function and then some visualization. So we can actually hook up Flink into this basically a stream and then reproduce the results on it. So we don't need actually any network or anything like that right now. So, sorry, I will put the Flink to work. So here I have 4 jobs. I will explain what all this does, just to start generating some results, so when we arrive there, we actually have something to see. Okay, so the main use case is basically generate insight and classify if the system is okay or not okay. That's what the main idea I want you to stay with. So how we actually do this? We get the data sources, right? We extract the information using logstars and some other components like Ceilometer from OpenStack. And then basically we aggregate all that information and push it into a single Kafka topic. This Kafka topic then is used as one of the main data abstractions. So we actually have chosen this because it actually allows us to flexibly add and remove Flink code and other tools for visualization later on. So actually Kafka gives us a very, very flexible architecture Plus, if you remember this ability to replay streams, it's actually very easy with Kappa, where you have something called offset that you can basically vary and then replay the events as they were coming in originally in the system. So we will plug Flink on it. Basically, we have raw data coming. We plug Flink. We do, and then you have seen that I have like 3 or 4 jobs running there. So what Flink will start is we'll start pulling some data and then pushing into different topics, different insights that it generates. And then we will be able to see those in Elasticsearch and Kibana. No. So this is how actually the logical data pipeline looks like. We start with the raw data. We do some preprocessing. This preprocessing jobs, actually what it does, it's start counting frequencies of logs. So if you actually think about it, it's very easy to determine if a system is misbehaving just because of the amount of logs that it's generating. So when some error occurs actually in a system, it will start generating error logs. And that means that the frequency of these logs will actually increase a lot in very short time. So actually, using that simple characteristic and pushing that to these feature vectors, we have already some interesting insight about the system and how it is behaving. And then we'll take that, and we'll apply this machine learning algorithm that I've been talking about. It's basically a streaming k-means, which calculates, if you're familiar with clustering, this will basically calculate how many clusters and where these clusters should be. So basically what it will say is how many types of nodes do you have in your system. And then the predictor will basically use that information coming from the streaming and then apply it to the feature vectors that come in real time, generating some insights saying that, okay, this system is okay, or, well, this system is not okay. And that also, there is another, if you look in the bottom, there is something called time drift. So why do we need this time drift if we are already classifying the system as okay or not okay? Well, the time drift is actually important for the pre-processing and actually knowing how is our data. In the pre-processing, I didn't say, but we actually are receiving events for a distributed system. So each system is generating its own records with its own clock. And that we basically need to know how much an order we can get the events from this source. So let's say that the time drift will give me a measurement of how many unordered events do I have in my system and how much they are unordered. So I can basically design a good working pipeline for the top part of the data pipeline. So I will just focus in these two. I will leave apart the machine learning apart algorithm, and basically show you, hopefully it, if it didn't crash. Yeah. Okay. So how many of you are familiar with Kibana? It's a tool that you have been, okay, so it's not the first time that you see this. So Kibana is basically attached to Elasticsearch. Elasticsearch is a database that is very good for aggregating data, right? So I can basically generate different views just with a very simple search on top of here. So what you are seeing here is basically that some events are arriving. And what are these events? These events are the result of the pipeline that I was explaining before. So I have cheated a bit this time. And I have connected not only the okay, not okay, and the time drift, but I also have connected basically the pre-processing results. So we can visualize the whole process and the whole pipeline. So I will show you two main dashboards. I will open this. Yeah. So, okay, it's not very complicated, this dashboard, but what this dashboard does is basically keeps track of, for example, how many logs we are receiving now per host. And you actually see that there is one that is completely out of sync with the other one. This can be because, okay, we are replaying the stream, or because in the real system it will mean that basically this can be the controller node. So if you think about it, in the cloud, there can be also different types of nodes, right? So this doesn't mean that actually the system is behaving, it's just that it's a different node from the other ones, which in this case can be the controller, for example. Right? The controller will generate much more load and much more, well, not load, but much more metrics and logs than the other ones. But also that's the normal state. It would be worrying if actually the controller is generating very few events compared to the other one. So what we are interested actually is, okay, knowing that that should be the state of the controller, can we actually say if that deviates from that or not? And that's what you are also actually seeing in this part of the dashboard. That you see K means erratic node clustering means that these two nodes are actually deviating from the normal state, which means that knowing the type of these nodes, they are actually misbehaving and generating another completely different result. Right. And then I will talk a bit about the time drift. So this is just to give you a view on actually how much these the events that we are receiving are in order. So basically around 10% of the events that we received from this simple setup, I mean, are actually an order. So what I will go later a bit more into details how this actually calculate this, but what you can see basically is that from a very simple setup, we actually get 10% of the stream is actually unordered, which means that, okay, we need to take care of this and we need to know how much these events are unordered. So that leads me to kind of a time challenge for you. So if I ask you, how would you count 20 seconds? Anyone wants to be brave to? Huh? Okay, well, that's one point, yeah. But what I will actually look is, well, I will look at my clock and count. So, but if I put it a bit more complicated than now, I mean, how would you count 20 seconds without your own clock? Then I will actually have to start asking a lot of people, and then each of you will tell me a different number. Each of you have a different clock, right? And I'm sure that none in the room has actually the same exact time as one to another. So this is actually what is happening in the stream. We are generating things from different clocks. So how can we actually have a single stream that takes this into account and then analyze if we actually are not following a sequential increasing clock? How can we do that? So, and that leads me to the time handling. This is basically what happens with event time when you use event time. You will not use your own clock, but rather you will rely that the information that comes from the records is actually correct. And you will use that for your analysis. So the difference between, I mean, if you have done some streaming already, you would know that in the processor time, you will basically use your own clock, and whatever you have to worry about is basically that you will have different clocks in your machine. So, well, each machine will have different, maybe windowing, slightly different, but well, you don't have that problem of synchronization. That's actually the default one, has been there for, it's available in many other, or at least the other streaming frameworks. But the interesting part is the event time. So why were we actually so interested in the event time for our use case? Our use case basically needs to count frequencies of logs. And that means that we really need to be able to be sure that when we count, we actually count the right number of events. So there is two things to consider here. Is the time drift, which basically means that how much should we wait to be sure that we are counting all the events from this time window. So let's say if I want to count the first 20 seconds, when should I actually execute so I'm sure that I'm not receiving as the event of the second 19. So that can be 25 seconds, that can be the execution at 30 seconds. So it really depends on where your data is coming from. And then another aspect is the unordered events that, of course, you don't expect that to be kind of sequential, right? I have already mentioned that several times. So. And then I put the watermarks. The watermarks is, I think Stefan and Costa has touched upon that already, that basically this is coming from the data flow model. And this, what it says is basically, it gives you a lower bound that tells you where you actually should execute. So how much time you should wait to execute that. That's what will be defined in Flink, and it's called watermark. So if my watermark is 5 seconds, let's say, if I want to count in the range from 0 to 20 seconds, I will be able to execute in the 25, because I know that after 5 seconds, I will not receive any events lower than 20 seconds. So this is how it actually looks a bit in the Flink implementation. You get a stream of events, right? You enable the timestamps. So what that will basically do is it will create tuples. Those tuples will be the time of the machine on the event. And then you basically implement your own extractor. So you will tell Flink how Flink extract the time from that particular record. That will be then the substitution then from the time that you had previously. And that then you can basically do the the window in operation and then start counting and doing basically your operator. So an interesting part that I have already mentioned is that, okay, this now will order using that time event. And then if you window, for example, I mean, you will then execute by the time that the window starts plus the size of your window plus this watermark that you have decided, so because you know already that you will not receive more events from there. And this is basically calculated in the time drift. That's why we're so interested in this component, so we can actually measure how much our events were unordered. So if I go back a bit, just a second. Okay. You will note that basically there is not a lot of events unordered, but also we are calculating here how much time this is actually unordered. So taking this, the next thing that we are trying to do, or we are thinking about, is basically, can we use something like this job to actually inject those variables directly into the event time handling inside Flink? So that can be a possibility, for example, for future work. So tips and tricks then. We got to know that this local deployment is something interesting. I mean, and why we actually deploy this. We are collaborating with SIG, right? And Ericsson is a bit protective in the sense that no one can actually go there and just connect to the network and then have everything available. So we had to find some way of actually collaborating and sharing the different basically jobs and parts. So what we do, we use Vagrant, that you have seen. And what we have built is especially the VM1, is basically a replay function where we use logstash. So logstash will basically take a data dump of this flow, and it will replay as it is a continuous string. And this stream will be input into Kafka, and that Kafka is available, is basically available internally in your local computer. So you can use your own environment like IDEA or Eclipse or however environment editor you're actually using, connect directly to Kafka and then try things out. The good thing of it is that it's quite simple. I mean, it's just a command that basically will boot the for our case, it will boot the visualization and this replay function with Kafka. So we actually not only try in the the algorithm itself, but also we try the serializing and the serializing parts of the jobs itself. So it's actually quite convenient. So what have we learned from using the latest Flink version? So we actually like it. It's a very natural candidate to address the Kappa architecture, which we believe will be much more common in the incoming months and maybe years. It has a very good integration with Kafka. We really like this optimization and the nice representation of jobs that you get from the cluster. And it's really easy to get going. So to start running your first cluster and basically start coding is actually quite easy. And things to improve, which, well, the first one is expected as we were working in a snapshot. So APIs varies quite a lot, at least in the snapshot version. And some of them are basically reverse order parameters that we have already told some of the community. So we hope that this is basically a minor thing to fix. So. And then the last one you can basically ignore, as I got to know through Stefan today, that actually you have built already some monitoring solution that gives you how much data it's analyzing and gives you much more contextual data from the cluster. So I think that's all from my side. So please ask questions, comments, whatever you have in mind.
It looks like you had your hand.
No.
I guess a question that is also connected to the previous interesting talk would be how well do you think that Spark with micro batches would work in this kind of architecture?
Well, it can definitely work. I mean, we have been using Spark as well in research before, and we have been able to generate some results. But actually, the latency we have seen that is much lower in Flink. That's one of the aspects that we like it. Another thing is that we were not able to do the event time window as easy, at least, as in Flink. So that's something that was really encouraged from our side to actually use Flink, that we actually can realize this kind of use case with very simple code. So that was a very big plus to Flink. I'm sure you can do it using a Spark streaming, but I don't think that in that easy way, I have to say.
Thanks.
Just comment. So Spark does not have any event time reordering. That is the reason, I guess. Flink is better for that.
Thank you.
Hello. The event time you assume is basically one source of events based on one single clock. Can you comment on if you have multiple sources of events coming from different, and then you merge into one stream? How do you manage the event time?
How do I manage the merging of multiple sources into one?
Yeah.
Okay. So that's actually managed by Kafka. I mean, you know, Kafka is divided by topics, right? And then.
No, I'm talking about the event time.
Yeah.
Like every source has its own clock.
Yeah.
So putting a timestamp on the event, right?
Mm-hmm.
How do you coordinate the?
How do I coordinate the time of the machines? Or?
Yeah. So
I mean, you have ways of coordinating the time, but it's not always accurate to the millisecond level. I mean, you have solutions like NTP or things like actually synchronize the clocks periodically, but actually that is even, if you go to the millisecond level, you will find that there is a big difference between the clocks, actually. Right. So when you analyze this at this kind of a speed, you actually need to drill down to the millisecond level, and there you will see difference. So there is actually, you need to reorder this or do something about it, because you actually see them unordered quite commonly. Does that answer your question? Or?
Yeah, I just wanted to comment.
That's it.
Well, okay, thank you.